This lecture is about backpropagation, a bit of the theory and background information as to why it works, and not really a full-blown general derivation, but a demonstration that will convince you that it does work and that it's based on the chain rule back through a network. So backpropagation is applied to feed-forward networks. And they have training pairs, so we're given a training pair with inputs I1 to I sub n, and then there are targets T1 through T sub m, and we calculate outputs of the network corresponding to that O1 through O sub m. So the network has this feed-forward structure, some hidden neurons. I'm only drawing one layer, but we could have multiple layers of hidden neurons. In fact, let's just go ahead and draw that. And then we have an output layer. So the inputs go in here. We got connections going forward. And then the outputs of these neurons get assigned to the outputs O1 to O sub n, O sub m. And then the targets for training for those are the T values here. So the first thing we do for this network is we define for a given training pair, inputs, outputs, and targets, we define a measure of the error. And this is measured at the output, and it's sorry, it's how the targets differ from the actual network outputs that are calculated. So we're going to call that E. And it's written as 1/2 the sum of all of the individual output errors squared. So this is a neuron number K, output error, and we square those and sum them all up. And this error is a function of the weights inside the network, right? We've talked about like there's W, I, J in here. And it's written as a matrix because Wij has the form of a matrix. It's I rows and J columns. So the error is a function of the weights, and in fact what we want to do is we want to minimize the error with respect to the weights. In other words, we want to find the best set of weights that makes the error as small as possible. And why are the weights in here? Well, of course, the weights are used to calculate the output of the network, and so inside O are the Wij values. And backprop is a numerical scheme or method called gradient descent that minimizes E with respect to the weights. And that's based on this formula, where if we apply a set of inputs, we calculate outputs, and then we calculate that error E, then we adjust the weights based on this weight update rule. Based on the gradient of the error E with respect to that particular weight. So you calculate the derivative of E with respect to a given weight, and then C is the learning rule like we've used before, so you take the old weight and you update it so that you go downhill, minus sign here. We go in the negative error gradient direction to get a new set of weights that should give a lower error. This is not easy to calc. because the error depends upon the outputs, and the outputs depend upon outputs of other neurons in hidden layers until we get down to the point where the weight actually shows up in the formula. So really, backpropagation is a form of the chain rule for differentiation. And that's what we're going to go through with a demonstration of how to calculate this gradient here based on backpropagation. So in summary, the error is a function of the weights. The outputs are in the error, and the outputs depend upon the weights. And so we're going to minimize E by going downhill in the negative gradient direction of E until we finally get a good set of weights. All right, so a demonstration of this. We're going to apply this to a really simple network. It has 3 inputs. So that's the input layer. It has 4 hidden neurons and then 2 output neurons. Ran out of room here, but you get the idea. This is O1 and this is O2. And then we have weights going from each neuron to the layer above it. So for this one, we can draw all of those in. And we want to number these neurons. So this is neuron number 1. This is neuron number 2, number 3, 4, 5, 6, 7, 8, and 9. And so we apply the inputs from a training pair, calculate all of the x's that are the outputs of all the neurons, and then we assign the output O1 to the activation level of neuron 8, and then O2 is the activation output of neuron 9. The weight that we're going to look at updating is this weight here that goes from 1 to 5. And again, that's why this is a demo. It's not a full derivation. We're just going to look at this weight and applying the chain rule and the gradient descent rule to that. So the first thing we do is we define our error. So there's our error of neuron 1. And here's our error of neuron 2. Add those together, and that's the total error. Next, we want to calculate the gradient, so we're going to take the derivative of the error with respect to W51. Again, we're just focusing on that particular weight. And so we're differentiating this, and the weight is going to be inside these outputs, because output X8 obviously depends on W51, and X9 depends on W51. So the derivative here is we're going to have 1/2, and we have the product rule, so we're going to have T1 minus O1, and then the derivative of what's inside, negative sign we got to keep there, and that's multiplied by 2 because of the square, and then same thing here. So that's just using the product rule on the square there. And now you can see why we put that 1/2 in front, because when you take that square and differentiate it, you get 2's that cancel out with the 1/2. So it just makes things easier. It really doesn't matter if we scale the output by the error by 1/2 or not. All right, so the next thing we need to calculate is this derivative here and this derivative here. So what's O1? It's x8, which is the activation function for that neuron, times the sum of its weighted inputs. Okay, so that's all of the inputs going to neuron 8. We've got the output from 4, the output from 5, the output from 6, and the output from 7 times the respective weights. So the derivative of O1 with respect to W51, where's W51 show up? It's not here. It's not here. Not here, it's not here. So it's got to be in the x's. So if we look up here, 5, the output from 5 is going to depend upon this weight, and none of the other ones do, because that's the weight from 1 up to 5. So it shows up in x5, right there. So differentiating, we get the derivative of f. We're going to call out that stuff inside. That's the terminology we've used before. That's the net input for neuron 8. So that makes it easier to write this. And then we end up with W85, and then the derivative of x5 with respect to W51. Okay, we still need to do this derivative here. So let's do that one. We've got this that's going to substitute in up here. We still need to do some work on it. So let's leave some space here, but I want to continue on with O2 is x9. It's the activation function for neuron 9 times the weights going into it times the signals. And just like O1, x5 is where we're going to find W51, so the derivative is going to be f prime, the derivative of that function, evaluated at U9, which is what we're calling all the stuff inside. And then the derivative of what's inside is W95. So you can see why we're chain ruling down through the derivatives, going inside each of the functions. All right, now let's go back up above here. And we need to list x5. x5, go back up and look at the picture. x5 is x1 times the weight plus x2 times the weight plus x3 times the weight. So we've got f5 W51 x5 plus W52 x2 plus W53 x3, and we could have stopped before that because here's W51 that we need to take the derivative of. So in fact now it's easy. The derivative of x5 with respect to W51 is f prime 5, and then this is U5, the net input, all the stuff inside there, is U5, and then going inside we have W51. Oh, my mistake. Get rid of that. The derivative of W51 with respect to itself is 1, and so we get X5 left over here. Well, that's a mistake. Let's go back. I wrote this wrong. This is X1. And this is X1. Yeah. My bad. Wrote the wrong number there. These are correct over here, W52 and 53. So that's what we need to plug in here. And then we plug this in up here, and then the same thing happens for this other derivative over here. So let's finish that one up. Well, in fact, we've already done it, right? There is exactly what we need. So that's the same thing that we need for down here. So let's collect it all together. So we're going back up to this formula, and we're plugging in for this derivative and this derivative that we just calculated below. So we're going to get T1 minus O1 plus F prime 8 U8 plus W8 5 plus F prime 5 U5 X1. So we're getting all of this stuff here, and this stuff here. Got to remember to grab that minus sign that we had up there. So we see that we have some common terms here. So we'll look at factoring those out. But then the secret to backprop is how you group some of this stuff together. Let me grab a different color. We're going to group this stuff here. We're going to call that delta 8. And we're going to grab this stuff here. We're going to call that delta 9. If you look back to the previous lecture, you'll see that backpropagation calculated these error deltas for the output neurons as delta 8 and delta 9. It's the target minus the output, and then we multiplied by f prime of the activation function for that neuron. So we're grouping those together and calling that the error delta for neuron 8 and the error delta for neuron 9. And then let's factor out this stuff here that's common. And using those definitions of delta 8 and delta 9, and here's our factored out term. And then we look at this and we see, well, this is the sum of the deltas for the output layer times the weights going up to the output layer from 5. And so this is the sum of the errors that neuron number 5 feeds out 2. And that's what we used in the formula for backpropagation. We said that in here, we look at the layer above the one that we're trying to calculate, and we sum up the deltas times the weights along the path. And this together, or let's grab another different color here so we can identify. Let's do red. Then we're going to call this delta 5. So the error delta of neuron 5 is the sum of the errors that 5 feeds out to times the weights that connect the neuron 5 up to that next layer. So if we do that and define that, then the gradient is a real simple formula that looks like that. Now that doesn't mean it's easy to calculate, because you've got to calculate the delta 5 according to its formula, and you've got to calculate the delta 8 and the delta 9 according to their formula. So it doesn't shortcut the calculation, but it groups it in a way that makes it easy to calculate. For each neuron, you calculate a delta. Delta 8, the output neurons are calculated like this. Any hidden neuron, its delta is calculated by looking at the layer above it and summing up the error deltas you've already calculated for that. So you can see that the calculation for the network, for the deltas, goes backward. That's why it's called backpropagation. The forward propagation was calculating the X's and the O's, and the backward propagation was calculating the deltas. And then we go back into our formula for gradient descent, which was way back up here. This is the gradient we were calculating. So we plug that into this formula to get our weight update rule. So when it's all said and done, W51 new is W51 old. Notice the minus here cancels out with the minus in the gradient descent. And this is the weight update rule. Now, if you think about the perceptron rule, this fits. This is the signal along the path. Of the weight. The weight goes from 1 to 5. X1 is the signal going into that path. And this is the error of neuron 5. And that is the backpropagation weight update method. You update the weights with this formula, and you calculate the deltas going backward through the layer. There's some issues that people discovered with backprop, and there are some fixes that people discovered. So I'm going to briefly talk about those. Maybe slow training. I'm going to write these and I'm going to draw a picture. May never train, or it may get stuck in what's called a local minimum. And these can be demonstrated by thinking of the error E as a function of just that one weight we're looking at. And draw an imaginary, we'll just make up an error surface that tends to illustrate some of this. So this is how maybe the error E varies if you plotted the error E with respect to all kinds of values for W51, you get this. Let's connect that up better. So let's say we have an initial value for a weight that we guessed at over here. If we calculate the gradient, it looks pretty flat. I've kind of drawn it maybe the opposite direction. So let's assume that it's flat. And since the derivative of W5 of the E with respect to W51 is pretty close to 0, it could train really slowly until maybe we march over to this point where then we start going downhill. And things are looking good, but then we get stuck at the bottom here of this local minimum. And this is characteristic of minimization problems and gradient descent because it goes downhill, but if you have these up and down bumps, it could get stuck. Whereas what we really want is the global minimum here. So we may get slow training if we have flat regions of the error surface, the E versus the weight. It may never train, or it may get stuck in a local minimum here. And so some of the fixes that people have looked at is you vary the learning rate. That number C, you start out big, so that if you're in a flat region like over here, you take big steps. But the problem with big steps is you may step back and forth here, or hopefully you take big steps and you jump back over here, but then you may bounce back and forth and never get to the bottom of this global minimum. So you start out big, but then you reduce. Start out with a big learning rate, and then as you go along, you reduce it to get smaller and smaller, so that eventually you find your way down to the minimum. Another thing is to add random numbers to the weights periodically. You can think of it that way. If you're stuck at the bottom of the local minimum and you add a random number to this, maybe you get bumped. Sorry about that. You get bumped over here, and then you can continue on down to a local minimum. Some people call this jogging the weights. Another fix is to add more neurons. These would be hidden, which gives you more weights. Which are parameters in the error surface. And by doing that, you get another direction. So if you look at this plot here, if we only had one weight in our network, there are lots of local minimum that it could get stuck in. But if you have another axis, say W52, then maybe this is a bottom here, but you could actually go downhill in the other axis direction. The more weights you add, the more options you have as far as going different directions and getting downhill on the error surface. Now, there are disadvantages to adding a lot of weights. The network gets really big, and often too many weights leads to overfitting, and we'll talk maybe more about that later on. All right, the last thing that I want to mention is something called a biased neuron. We've been drawing our network to look like this. So that network we just dealt with had 4 inputs, and I forgot how many hidden neurons did we have in that demo. We had 4, and we only had 3 inputs. And we only had 2 outputs. I'll get this right. So this was that demo network we were just deriving backprop for. If you look at networks in a lot of textbooks, you'll find out that there's another neuron here that's often labeled neuron number 0, where this is 1, 2, 3, on to neuron number 9 like we did before. And this neuron always outputs a 1. And it's got connections to every neuron in the network, except for the input neurons. And this is called a bias neuron. And here's what this bias neuron allows us to do. Let's look at output O1. There we go, I got all of those. So we have the sum of the weighted inputs going into neuron number 8. If for some reason I1 is 0 and I2 is 0 and I3 is 0, then all of the x's, x5, x6, x7, even x4, sorry about that, those are all going to be 0. Because the inputs are 0, multiplied by the weights, you get 0. And so if you have all 0 inputs, you can't get a non-zero output. Because all you're going to do is get zeros in this summation. The addition of the bias neuron changes this to this formula. And let me add in number 4, which I forgot last time. If we're adding in the bias neuron, then we get another term here that's W80 times 1. Because we said the bias neuron always outputs a 1. And you can see what this does. Even if x5, x6, x7, and x4 are all 0, we can still have a non-zero output with this weight here. Effectively, what that does is it shifts the activation function of that neuron. So let's say we have this tan-H. With a tan-H, you put in a 0, you get a 0 out. But if we add in this shift here, then it effectively creates a shift over to a value t, and then we get tan-H shifted over by that amount t, where t would be the shift that's adjusted by the bias neuron. And we train that weight from the bias neuron just like all the other ones, so you can actually train the amount of shift you need for your activation functions to get a lot more generalization, a lot more ability to do calculations.